Okay, so this is the second lecture on diagram groups, and so we will use a perspective which will be more geometric. So if you remember the definition of diagram groups, it was essentially combinatorial, I mean, in a way which is actually rather similar to free groups. You know, I mean, and maybe I will start with some comparison between diagram groups and free groups. So free groups are defined by words up to free reduction, and the product is just the concatenation of words. Okay. And in a similar way, diagram groups are made of, so elements of the group are diagrams. You have a notion of dipole reduction, and the product of diagrams is just, again, the concatenation. Okay. So, loosely speaking, one can say that diagram groups are like free groups, but in 2 dimensions, in some sense. Okay, so where is the geometry in everything? So for free groups, we know that they act nicely on some trees. I mean, if you take a free basis, then you look at the Cayley graph, and you have an action by left multiplication, and the Cayley graph with respect to a free basis turns out to be a tree. And by using this nice geometry, you can deduce some useful information about the free group. And there is something similar here. And so this is no longer a tree, but it's something which is not too far away. It's a median graph. Okay, and my goal today is to explain how you can what is first a median graph, okay, and how you can construct such a graph from a diagram group, or you can define an action, and how you can use this action to deduce some useful information on the group. Okay, so maybe I will start with some crash course on median graphs. Okay, so maybe to fix the definition, for me a graph today will be is just a set. Let's say a graph X and Vx, or anyway. So it's just a set with a relation which is symmetric and anti-reflexive. Okay? So, okay. So a set, so it will be, an element of this set will be a vertex. And the relation is, defines the notion of adjacency. Okay? So in particular, from a geometric point of view, a point of a graph is really a vertex. So I do not imagine edges like being like existing at all. They are just relation between vertices. And so given a graph, the distance, so for all vertices, let's say A and B. So the distance between A and B is the smallest length of a path connecting A to B. Okay? So a path is just a sequence of vertices such that any 2 consecutive vertices are adjacent. So with respect to this relation. And okay, so for today, all graphs are connected. Because I want to do some geometry, so I want my metric to be a metric. And in particular, I want this quantity to be finite for any two vertices. And if I take, of course, if my graph is not connected, and if I take two vertices in distinct connected components, I have no path between the two, and this quantity becomes infinite. And it's not something I want today. So for today, all the graphs will be connected. Okay, so now what's a median graph? So definition. So a connected graph or graph is median if for all vertices, say x1, x2, x3, graph x, there exists a unique vertex. So a unique, so it is called the median point. So what does it mean? It means that the distance between xi and xj is the distance between xi and the median point plus the distance from the median point to xj. And this is true for every I distinct from j. Okay, so that's the definition. The intuition to have in mind is that we have three vertices. Okay, and what we want is that there exists one vertex and only one, such that the distance between, say, x1 and x2 is equal to the distance between x1 and m plus the distance between m and x2. And the same thing for all the three possible configurations. Okay? So an example which should be clear is trees are median graphs. Because if I take three vertices, then typically they will delimit a tripod. Okay, and the center of the tripod is exactly the median point. So this is, yeah. Yes, it has to be unique to be median. It has to be unique. Okay, so the property of being median is also stable under a product. So if you take a product of median graphs, it's also a median graph. So products of trees are other examples of median graphs. So this includes, for instance, the grid. Okay, this is an example. Yes?
Can you show an example where you don't have uniqueness?
Sure. So, now an example. So, for instance, if you take the graph, this one, so this is K23. So, in this case, you have, you take these three vertices, and you have two median points, this one and this one. This is an example of a graph which is not median. So in this case of the grid, let's say I take this vertex, this one and this one. Then you can always find a median. So the median will be just, you take on each, this is the product, so on each coordinate you take the median. And what you find is, so on this factor, the median is just this point, and on this factor, the median is just this point. So your median point is this one. And you get something like this. Okay. So you also have cubes of arbitrary dimensions. So they are, again, they are product of trees. I mean, they are just product of edges. Okay.
Sorry, just to understand the grid example. So if I have just a line graph with just one dimensional grid, so the unique median point is just the point that it's between the other, right?
So if you have yes, okay, so on this, yes, okay, on a tree, in this case I took 3 points in some generic configuration, but if they are just on a line, then in this case the median point is just the
Middle one.
One of these three that's between the other.
sorry.
Just checking this.
Mm-hmm.
The median one is the one out of the three that's between the other.
Exactly, exactly.
And the grid is the product of two lines.
Yeah.
So it's
Exactly. Other questions on the definitions? No?
You have examples that are not products of trees?
Sure. For instance, you take some. You can do something stupid. You take two examples and you glue them. So, for instance, take a cube. And you add, I don't know, an edge. This is no longer a product, and it's still a median graph.
And besides?
So okay.
The cycle.
So the cycle is not an example, because so in the list of non-examples, if you take, let's say, for instance, I don't know, a hexagon, then what is the median point of, say, this one, and this one? There is no median point. There is a hole in some sense. So, but a 4-cycle is a median graph, right? Because this is an example of a grid, a very small grid. And this is the only cycle which is median. So a triangle is not median either. Not median. Because if I take the 3 vertices, there is no point in the middle to be the median point, basically. Okay, yeah.
Maybe a quick question, but is there an implication or link with delta hyperbolicity?
Not really.
Okay.
Okay, actually, yes. Okay, but it's a long story, so maybe I should not start on this subject. But okay, but something I can say is that a median graph may not be hyperbolic, and a hyperbolic graph may not be median.
Okay.
But there is some from the point of view of large scale geometry, there is some connection. Okay. Okay, so speaking about geometry group theory, a remark. Because if you come from geometry group theory, maybe you already met median graphs, but with another name. And they are the same. So a cube complex is just a space obtained by gluing cubes together, cubes of arbitrary dimensions. Okay? And so the word cat0 means that you can put on such a space a metric which in some sense looks non-positively curved. So on each cube, so each cube has a metric, it's a Euclidean space, okay? And you extend this metric to the whole cube complex, and you want this metric to be cat0, so satisfying some condition I don't really want to describe today, but which means that essentially the space has some flavor of non-positive curvature, okay? And so there is a close connection between the two, and actually the two families of spaces are basically the same. So if I take a cat0 cube complex, I can look at its one skeleton, and its one skeleton is always a median graph. And conversely, if I take a median graph, then I can look at its cube completion, which is a cube complex obtained from the graph by just adding cubes whenever you want, you can. So each time inside the graph you see the one skeleton of a k cube, then you fill in with a k cube. Okay? So you get all the cubes you possibly. And so the cube complex you obtain is always cat0. Okay? So in geometry group theory, the terminology which is the most used is cat0 cube complex, but today I will speak about median graphs, and this is a better terminology anyway. Okay, okay. So the idea to keep in mind is that in some sense, median graphs are non-positively curved. Okay, this is something which is useful to keep in mind. Okay, there is something really geometric behind. Okay. Something I would like to say is, so this is a definition of median graph, some examples. There is one tool which is really useful to study median graphs. It's a notion of hyperplanes. So I will write a definition. So a hyperplane is an equivalence class of edges. Is a class of edges. Yeah. Okay. With respect to the reflexive transitive closure of the relation that if you take a fourth cycle, then you identify two opposite edges. Okay, so this is kind of a notion of parallelism. Okay, so I will give an example. So let's draw some more or less generic okay, so this is a median graph. If all the edges are here, right, it's okay. There is an edge. Okay. So what's an example of a hyperplane? So it's an equivalent class of edges. So let's start with some edge. Let's say this one. And what I want to do is to add an edge in the class each time I see a fourth cycle, and there is the edge is opposite to the edge I already have. So for instance, for this particular edge, I see a fourth cycle here. So I know that this edge has to be in the class as well. But I also have a fourth cycle here. So I also have this edge. And I keep going. So I have a fourth cycle, this edge, this edge, this edge. And that's it. This is an example of a hyperplane, right?
Sorry?
Yes?
Are all median graphs the same by doing cubes?
Yes, in some sense, because you have this equivalence.
What's cube complex?
Yes, but at least cube complex. So it's a space made of cubes.
Okay.
So in some sense, yes. You can always obtain. So there is also a characterization. So median graphs are exactly the graphs that can be obtained from a cube, possibly infinite, by retraction. So there is really a close connection between median graphs and cubes. And in particular, you have this proposition. So yeah, so this cube complex, and in particular, it is simply connected. So it's a way to say that if you fill in the cubes, you get something simply connected. So everything is made of cubes. Okay, so let's take another hyperplane. If I have this edge, I see that I have 2 4 cycles here. Another one here. Okay, so this is another hyperplane, maybe a last one. If I take, so for instance, let's say this one. An equivalent class with a single edge. Okay. So you see that when you compare distinct hyperplanes, they can interact in some different ways. So, or maybe I need another one. Yes, sorry. Otherwise, I need some. Let's say this. This one. Okay. So the blue and red hyperplanes are transverse. Okay, so what does it mean? It means that it's possible to find a 4 cycle such that I have 2 opposite edges in one hyperplane and the other 2 opposite edges in the other hyperplane. Okay, this is what I mean by being transverse. Okay, but I also want to say that if I take the orange and blue hyperplanes, so they are tangent. So why they are tangent? It's because it's possible to find 2 edges, one each hyperplane, such that so they intersect, they have a common endpoint, but they do not span a 4 cycle. Either they span the 4 cycle, and in this case they are transverse, or they do not, and in this case they are tangent. Okay, but they have to intersect. So for instance, if I take the green hyperplane, it is neither transverse nor tangent to all the other hyperplanes, so orange, red and blue. Okay? So why are hyperplanes important? It's because in some sense, so the geometry of a hyperplane, so we have the median graph, is encoded in the combinatorics of its hyperplanes. Okay, so roughly speaking, if you understand the hyperplanes and how they interact, okay, then you understand how the geometry of your space. Okay, so maybe I will state one theorem going in this direction to motivate this claim. So let X be a median graph. Then I have the following statements. So first, for every hyperplane, so the graph obtained by removing all the edges from my hyperplane, obtained by So such a graph has two connected components, always. So they are naturally called half spaces. And they are convex. So on this example, for instance, by removing the edges, I mean that I remove just the edges. Okay, I do not touch the endpoints, the vertices. So if I remove the orange edges, indeed I get two connected components, one on this side, one on this one. And if I remove the blue edges, I again get two connected components. Okay. So that's the first point. So there is no geometry in it, just with context. But so another is so it makes sense to say that a path crosses or not a hyperplane. So a path is a geodesic. So it has minimal length, geodesic, if and only if it crosses each hyperplane at most once. And a consequence is that for all vertices, the distance between my two vertices coincide with the number of hyperplanes separating x and y. Okay. So I can really recover the metric just from the hyperplanes. Okay. So maybe let's consider an explicit example. If I take this vertex and this one, so x and y. So the distance between x and y, so in this case it's easy to compute, it's 1, 2, 3, 4, 5. So there must exist exactly 5 hyperplanes separating x and y. So you see that there is a blue one, the red one, the orange one, so that's 3, and there are 2 others. So you have this one, and you also have this one here, cutting the cube, right? Okay. Okay, so this is basically what I want to say about median graphs. Now I would like to explain how to construct median graphs from diagram groups. Okay? Okay, so 2. Okay. So remember that I told at the beginning of the talk that there is a connection between diagram groups and free groups. And how is a tree obtained from free groups? It is obtained just by, so this is a Kelly graph. So a vertex in the tree is just a word, or an element of the group. It's a reduced word. And the construction will be basically the same for diagram groups. A vertex of the graph will be just a diagram, okay? So, okay, so maybe I will just write a definition. First, maybe a statement. Okay, yes, a true statement. So, let P R be a semi-group presentation. And W a word. Then the diagram group dpw acts freely on the median graph. Let's call it MPW. Okay, and now I would like to define MPW. So, before defining MPW, I will define MP. So, let MP be the graph. So, I want whose vertices are the diagrams up to dipole reduction. Okay, so basically the same thing as for the free groups. And now whose edges connect delta, so class delta, to delta concatenating with something, and where A has a single two cell. Okay, so for free groups, the Cayley graph is obtained by, so the vertices are just the element of the group, and you move in the graph by right multiplicating by some generator, right? So in this case, so I add just one letter to the right. In this case, I take my diagram, okay, and what I do is that I just add a two cell at the bottom, okay? So that's the definition. Maybe I will give an example right away.
Sorry?
Yes?
What is that two cell?
So a two cell is, so in the diagrams, so I will give an example. That's better. Okay, so let's consider this semi-group presentation, so the same as before. Okay, and now I want to construct this graph, at least a piece of this graph. Of course, the graph is infinite, so I will just draw a piece of it. So I will start with one diagram, the simplest possible. Let's say that I start with a diagram with no cell. I will take the same as in my notes. So A, B, A, A. Okay, so now this is just one vertex of my graph. And now the neighbors are obtained by adding two cells. So what does it mean? It means that I want to apply a substitution coming from my semi-group presentation. So I glue something below, and for instance, I will apply, I need to draw it in the correct way. Left and right. So for instance, I have A, B, A, and I already forgot what I just, yeah, this one. So it's what I mean by a two cell, right? It's something like this. So it's one neighbor. I add one two cell at the bottom. But of course, it's not the only possible choice. Okay, I can, for instance, add this one, A, B, A. This one. Okay, or I can add A, B, A. This one. or I can add A, B, A, as this one. And I think that's it. No, that's not it. Okay, anyway, it's 4 possibilities. There is one more, but anyway, there is. Okay, otherwise the drawing will be really bad. So you have 4 neighbors. Okay, so that's just a little piece of the graph. But now my claim is that, of course, this will be my median graph, right? Yes.
So I thought that the vertices were supposed to be diagrams.
Exactly.
But these are just words, right? I mean, like.
This is a diagram, right?
Oh, okay.
Yeah.
But you say word on the top and bottom.
Yeah, right. That was my question.
We were told yesterday that
Mhm.
You don't have a base point W.
we were told yesterday, I think I understood correctly, that the top and bottom should have the same word.
Yeah.
They are the same to define spherical diagrams to define the group. But a diagram, in full generality, there is no restriction.
Okay.
So
each vertex is not necessarily doesn't correspond to an element of the group.
right, and that's the difference. Okay, maybe I understand why it's confusing, because for 3 groups, each vertex is an element of the group. It's no longer the case here. It's a diagram, but not necessarily an element of the group, because it's not spherical. You do not have the same top and bottom paths. Right. Yeah. Other questions on? Maybe I will keep drawing, and you tell me if there is something not clear. Because so the point is that it will be actually not really median, but almost. But there should be some cubes in it, okay? And we see that there are some cubes because in this case you glue something here, and to go over there you glue something here. But you can do the 2 at the same time. And what you get is this diagram. AA and this one. AA. And you see that there is a square, a 4 cycle. And with this guy, if you add, you will see a cube. So a 3 cube. So A, B, A. I glue this one and this one. And there is another one here. A, B, A. And this one, you have something here, something here. And the last one, when you put everything, so you have A. Okay, and you have a 3 cube, right? If you can see it. And okay, so maybe something I should say. Let's say I start from this vertex. I want to add a new cell, right? So something I can do is add a new cell. So I want to transform BA to AB. So what I get is okay. So that should be a neighbor of this one, right? But I have a dipole reduction, and my vertices. So I only draw diagrams, but to be precise, they are not diagrams. They are classes of diagrams up to dipole reductions. So this diagram is the same as this one. Okay. So actually, when I add these 2 cells, I'm just going back to my initial point. Okay. And it's how I draw my my graph. Okay. But there is something which is not so. It's not so. It's almost a million graph, but not quite. It's because this graph is not connected, typically. So there is a fact. Is that so delta 1? If you take two classes of diagrams, so they are in the same connected component. Of M of P, if and only if they have the same top path. So it should be easy to see.
Top and bottom are symmetric, no?
No. Not in this case, because I look at all the possible diagrams, not only the spherical one. So in this definition, I'm not asking the top and the bottom to be exactly the same. In the definition of the group, yes, but not in the definition of the graph. Okay. So one direction should be clear. So yes.
In the theorem, it's M of P on W. In the definition, it's just M of P. It's not yet defined M of P and W.
Yes.
Okay.
Yes. It's because my graph is not connected, so it's not the graph I want. So actually, MPW will be a connected component of M of P. Okay, so one direction should be easy. It is that if it is in the same connected component, then they have the same top path. And it's just because by very definition of the graph, I just move in one connected component by gluing something below. So I do not modify anything above. Okay? So if I have a path from one diagram to another, then necessarily the top path should be exactly the same. So this is just a consequence of the definition, basically. And for the other way, so if you imagine that the two, so I want to put that there is the same connected component under this assumption. So I need to construct a sequence of two cells such that I can glue them below delta at 1 to get delta 2. Yes?
This isn't a complete connecting component, right?
Sure.
You also change BA into AB and obtain the new part of it.
Yeah, yes, of course. So typically the graph will be infinite.
Yeah.
So I will always draw pieces of the graph. Okay, so if so what I want to do is to say that delta 1 is delta 2 times something, right? I want to obtain delta 1 from delta 2 just by gluing something below, so by right multiplying by something. Okay? But, okay, this is something really stupid to say, is that this is delta 2 minus 1, delta 1. And that makes sense precisely because I have this condition. Okay? Because the concatenation it makes sense only if the bottom path of the first factor is the same as the top path of the second factor. And the bottom path of delta 2 is the top path of delta 2 minus 1 is the top path of delta 2. So I get exactly this condition. Okay? So that's the proof of the fact, basically. Okay, so now I can finally define MPW. So So MPW is the connected component of MP containing all the diagrams with W at the top. So let's say 1, which is the simplest, just this one. But actually I will obtain all the others. Okay. Okay, so my theorem tells me that first, so this should be a median graph, and I'm supposed to have an action of the diagram group on it. Okay, and yes, so the action should be clear, right? So dPW acts on MPW by left multiplication. And this is well defined because so we know that all the vertices of MPW are given by diagrams with W at the top, but an element of my group is a spherical diagram with W at the top and at the bottom. So the left multiplication is well defined. That makes sense. And the action preserves the structure of the graph, because if I have two adjacent edges, it means that I can glue something at the bottom, but it's independent of what I do at the top. So the action sends edges to edges and non-adjacent vertices to non-adjacent vertices. Okay. So yes, so some remark. So okay, I'm not going to justify why this is true, why it's median, because it requires some work, but it is. So MPW is a median graph. You have an action which is defined exactly by left multiplication, and the action is free. So the fact that it is free is exactly for the same reason in Cayley graphs. I mean, you are just acting by left multiplication. So if you fix a vertex, then you must be the trivial element, just by the cancellation property. So maybe I would like to add two remarks. Because this graph can be thought of from different point of view. So the first one is that MPW, it coincides with the one skeleton of the universal cover of the square complex defined yesterday. Okay? So we saw yesterday that dPW is isomorphic to the fundamental group of some square complex, the square complex. But now if you take this complex, you take the universal cover, and you only keep the one skeleton, you get a graph, and this graph is exactly the same as this one. Okay? This is one different point of view. And another one, which is essentially what I just said, but with some big words, is that MPW is a connected component of the Cayley graph of the groupoid of diagrams so up to dipole reduction always. And so with respect to some finite generating set, so to the diagrams with only one cell. So that's just a fancy way. Yes?
Yesterday we defined the square complex, but not based on the word.
Okay. In this case, so SPW is a connected component of SP containing W. Okay, so this is really just a fancy way to say what I just said. Okay, I do not have for three groups I have a group, so I have a Kelly graph and everything is fine. In this case, I do not have a group, but I have something really close. I have a groupoid, which essentially means that I have a product, I have inverses, I have natural elements, but the product is not always well defined. But that's the only difference between a groupoid and group. Otherwise, everything makes sense. So I have a generating set, which is just a set of diagrams with only one cell. And I can look at the Kelly graph with respect to this generating set. In the groupoid, the Kelly graph is not necessarily connected, so I have to choose one connected component. I choose the connected component containing the natural element, let's say, just the W, so the diagram with no cell. And I get exactly the same construction. But I think this is a point of view which is rather, which is nice. It's interesting. Okay. Are there questions on all this construction? Okay. Okay, so far we have a group, we have a space, we have an action, and we are supposed to be able to extract some information from this data about the group. So what can be said about diagram groups by using these actions? So let's consider some applications. So it will be essentially a list, unfortunately. So first thing is that a diagram group with no z square is locally free. So by locally free, I mean that every finitely generated subgroup is free. Okay? So in particular, this prevents many groups from being diagram groups. So if you take, I don't know, the fundamental group of your surface of genus G at least 2, so genus at least 2, then this is not a diagram group. Because it's a group with no z square, but it's not free. It's not, and it is finitely generated. So it's not a diagram group, for instance. And it's possible to prove this statement by using this action on the median graph. Something else. So there is some dichotomy in some sense, is that if you have a group, a subgroup, which is not too far away from being abelian, then actually it has to be abelian. There is a gap in all the possible behaviors of subgroups. So every nilpotent and polycyclic subgroup in a diagram group is free abelian. Okay. Sorry?
Is there some cheap alternative or?
Not really. The point is that, for instance, you have Thompson's group F. So it is a diagram group. It is not close from being free abelian at all, I mean. And it does not contain a free abelian subgroup. So the precise this alternative is not satisfied by diagram groups. But now there may be other types of alternative which may hold, but I don't know any, so I don't really know. Okay. So yes, some example, for instance. So let's say, so the Heisenberg group, for instance. So not a diagram group. Okay. So you have this statement for nilpotent and polycyclic groups, but you cannot have something better. I mean, you have meta-abelian groups that are diagram groups. So for instance, if you take the risk product with Z with Z, so this is a diagram group. And it is meta-abelian. So the point is that if you are rather close from being abelian, you are abelian, but so there is a gap. But you have also examples which are considered as not being too far away from abelian and which are not abelian, that are examples of diagram groups. Okay. Third point. So if P is a finite presentation of a finite semigroup, then dPW is of type F infinity. So what does it mean? It means that it admits a classifying space with finitely many cells in each dimension. So this property is usually called the finiteness properties because so your group is finitely generated if and only if it admits a classifying space with finitely many one cells. It is finitely presented if and only if it admits a classifying space with finitely many one cells and two cells. And so you can keep going, and eventually you get something really strong, a finiteness property which is really strong, and you can deduce from the action on dPW on, so not exactly actually the median graph, but that on its cube completion, and by using some argument coming from more theory, you can deduce that there exists such a classifying space. Okay, and for instance, this property, this statement applies to Thompson's group F. Okay, remember that in this case, P, the presentation is just one generator and the relation is x equal x squared. Right? So this is a finite presentation of a finite semigroup. So from this statement, it follows that F is of type F infinity. All right. But there are not all diagram groups are of type F infinity. For instance, if you take, so this one is finitely generated but not finitely presented. So it does not admit such a classifying space. Actually, it does not admit a classifying space with finitely many one cell and two cells. So it's specific to one particular family of diagram groups. Okay, another one. So if the class of W is finite, so by the class of W, I mean the set of all words equal to W in the semigroup. Okay? So if this class is finite, then GPW is a subgroup of a right-angle arcing group. And for instance, it is linear over Z. Okay. Do I need to write the definition of a RAG? Yes? Okay, so definition of a RAG. Alors, let's say gamma is a graph, so not necessarily connected. So actually, when I say that all graphs are connected, I lied. So let gamma be a graph. Then the right-angle arcing group A gamma is defined by the following presentation. So the generators are just the vertices, and the relations are commutators. And I want to say that two adjacent vertices commute. Okay. So the idea to keep in mind is that if there is no edge, A gamma is free. Right? Because I do not have any relation, so my group is just a free group. If gamma is complete, then A gamma is free abelian. Right? So if gamma is complete, it means that any two generators commute, and so I get an abelian group. And usually what we say is, so you have two extreme situations. When you have no commutation, so you have a free group. When you have commutation everywhere, you have a free abelian group. And everything is between is just a family of RAGs. So it's some sort of an interpolation between free groups and free abelian groups. Okay? And so there are very nice groups. And so what the claim here is about is if I have this assumption that the class of W is finite, then my group will be isomorphic to a subgroup of a right-angle arcing group. Okay? So in particular, all the nice properties I know about RAGs and that pass to subgroups will be automatically satisfied by these diagram groups. And in particular, being linear over Z. Okay, so being isomorphic to a subgroup of a matrix group with Z coefficients. And again, it's true only for some diagram groups. So for instance, again, Thompson's group F is not a subgroup of a RAG because it is, for instance, it is not linear. I mean, it's not even residually finite. Okay, maybe another one. And a part of this statement will be proved in the exercises. I mean, if you have a group acting on a median graph, you automatically have a morphism from the group to a right angle, so not Artin groups, but Cox-Setter groups. But just add a relation, you put u squared equal 1. You always have a morphism. And so, of course, in general, this morphism is trivial. You cannot say anything in full generality. But under this assumption, you can use a specific property about the action to deduce that this morphism will be injective. Okay. So every diagram group satisfies a short zigzag sequence let's say G. Okay, so you have a short zigzag sequence, and what is Q? It is a subgroup of Thompson's group F. And what is N? It's a subgroup of a right angle Artin group. So this statement tells you that in some sense, every diagram group can be constructed from subgroups of RAGs and subgroups of Thompson's group F. Okay, so this is a very strong decomposition. On the other side, the class of subgroups of RAGs is really huge. We do not understand them. And the class of subgroups of Thompson's group F is really huge, and we do not understand these groups. So it's an interesting statement, but it does not mean that we understand everything about diagram groups just from this short zigzag sequence. Something interesting is that it allows you to construct subgroups of F, because if you have some diagram group and you are able to show that this kernel must be trivial, then you have an embedding inside F, and you can construct some non-trivial subgroups of F by using this short zigzag sequence. So this is a rather nice statement anyway. Okay. Maybe another one. So if P is a finite presentation, then dPW satisfies the Aguirre property. So it means that there exists a proper action by isometry on a Hilbert space. Okay, so it's a property that basically tells you that there is some compatibility between the geometry of the group and the geometry of Hilbert spaces. Okay, that you have proper action on a Hilbert space. And you also have, so there are also some other motivations. I mean, Aguirre properties also imply some conjectures with big names that virtually nobody understands, but okay, so you have this name. But formally it's really this. I mean, the intuition is really that you have some compatibility between the geometry of the group and the geometry of the leader spaces. Okay, so do I have time for something else? Okay. Okay, so we talked about diagram groups, but there are also some generalizations. No. So, okay, theorem. So Rachel mentioned that there are also other types of diagram groups called symmetric and braided. So symmetric diagram, we say respectively braided. So they act on a median graph, on median graphs. With finite, respectively, braid groups, stabilizers. Okay, so maybe I should put an example of a diagram. So I will consider always the same presentation. It's convenient. So for example, an example of you have A, B, A. So using the formalism of transistors, what I can do is something like this. So you have BA. So the transistor corresponds to applying a relation for my semi-group presentation. Okay, so AB becomes BA. But and I can, for instance, also add this one. Okay, so A square become A, and I can just permute. So this is a symmetric diagram. And you can do something similar by braiding the strands. So for instance, you have something like this. Okay, and this is a braided diagram. Okay, so for these generalizations, you can also modify a little bit the construction to get an action on the median graph, but it's no longer free. For symmetric groups, the stabilizers, so they're no longer trivial, but they are finite, which is not too bad. And for braided diagrams, you get an action. So in this case, the stabilizers become infinite, but they are well known. They are isomorphic to braid groups. So they're infinite, but you understand them, which is not bad either. And so maybe one consequence of this.
I guess the stabilizer, in the symmetric case, the stabilizers are finite, but not uniformly finite.
No, exactly. They are not uniformly finite, and this helps me for the transition, actually. So the consequence of this statement is that in symmetric diagram groups, torsion finitely generated torsion group, torsion subgroups are finite. So, which is not obvious precisely because usually you do not have a uniform bound on the size of finite subgroups. So the typical example is when you take the presentation for Thompson's groups. So in this case, you do not have F anymore, you have Thompson's group V. But you can see from this example that you have a lot of big symmetric groups, because if you take you apply presentation, you apply your relation x equal x squared again and again to have many wires. Now you do some permutation, and you just do the same thing again, but in the reverse way. And when you take, so this is a subgroup isomorphic to the symmetry group. So in this case, this is S4, but in general, you can get a copy of Sn for arbitrarily large n. Okay, so in particular for so V, which is dpx, you obtain arbitrarily large subgroups, and actually you can find a copy of an infinite torsion group, S infinity, basically. But if you restrict your attention to finitely generated torsion subgroups, then they must be finite. And they must be finite because you have this action, and this median graph is specific. So the idea is that in this median graph, you do not have infinite cubes. You may have cubes of arbitrarily large dimensions, but nowhere you have an infinite cube. So if you have a sequence of cubes of increasing dimensions, the cube has to go to infinity. Okay? But if you fix one vertex and you look at what happens around, you never see an infinite cube. And with this assumption, this is the theorem, it's not at all obvious, but if you take a finitely generated torsion subgroup, you make it act on such a median graph, and you must stabilize the cube. And because the stabilizers are finite, you conclude that your group must be finite. And so you cannot find an infinite such subgroups. Okay? And so maybe one word about the construction. So the construction is basically the same, but you have to be careful about permutations of wires. Okay? So the only modification is vertices are diagrams modulo dipole reduction, and you are also allowed to permute the bottom wires, okay, and permutation of bottom wires. So for instance, if I take the same presentation. If I consider okay, so this is a diagram, and if I take the class of this diagram, modulo dipole reduction and permutation of bottom wires, so this will represent the same vertex as this one. And this is the only modification which is needed to make the construction work, so to get a graph which will be median. you take exactly the same definition, more or less the same proof. It's slightly more complicated, but it works. And you get a median graph with an action, and you have a non-trivial vertex stabilizers because precisely of this permutation. They are finite because you are allowed to permute the bottom wires, and so the stabilizer of this vertex will be precisely a copy of the symmetric group of three elements, which correspond exactly to the 3 bottom wires. Okay, so it explains. And for braid groups, same intuition. So permutation. So you just braid the bottom wires. Do the same thing again. It works. You get an action on median graph, and the stabilizer of vertices corresponds to the braid groups on the bottom wires. Okay, so basically the same idea. Okay, so maybe I will stop now. I have nothing else to add, I guess. I can add something, but maybe not. Not reasonable. No, I will stop now. Thank you.
It works. So do you have questions for Anthony? We already asked some, but so I rush with the microphone.
So you said in the beginning that the action of your diagram group on your median graph is free.
Mm-hmm.
When is it co-compact?
So it's co-compact. Is it written? No. So it's co-compact precisely when this class, the class of the world, is finite. So co-compact if and only if the class of the word is finite. So this is a set of all the possible words equal to W in the semigroup. So for instance, for this one, it does not work because you have A, which is equal to A square, A cube, A4, etc., etc. And so this is not, the action is not compact. But for instance, if you remove this relation, then it becomes compact because you can only just permute letters and it works. And yeah.
Other question?
Yeah, it's in.
So you said that the calligraph, the median graph is the calligraph of the groupoid.
Mm-hmm.
Can we see the calligraph of the group in the median graph?
I don't think so. Because the problem is that, of course, the generators are not generators of the group. And I'm not sure you can see it from... so not obviously, I would say no, but I'm not sure. I mean, it's difficult to say that something does not exist, of course. But my intuition is that it's not the case.
Other questions? So maybe I have 2 questions. Just a naive one. Can there be torsion in the diagram group?
No.
No.
Because of the fact that it's not written. So it's due to the fact that the action is free, basically. So free not on... Okay, to be precise, the action is more than free. You have that cube stabilizers are trivial.
Okay.
So the action is not only free on the vertices, it's also free on the cubes.
The cells.
And now if you take a finite, for the same reason as before, if you take a finite subgroup, it will stabilize the cube, and so it will be trivial because the stabilizer of the cube is trivial.
And another question, your short exact sequence,
Mm-hmm.
Does it have something to do with Cronrod's theorem of decomposition of semigroups?
Not, I would say no. At least it's not proven using this this theorem, but maybe.
So, how can you say a few words about the orderability, either left or by, now that you have discussed these median graphs? Maybe do you see the? So, what is the action on the? I'm interested in the perspective of action on the real line. So do you somehow get a line somewhere in this graph, or?
Okay, so I can say only two things. The first one is, so we know that the groups are biordurable, but not in an explicit way. We do not have an explicit order on all these groups. What we know is that, there exists some diagram group, let's say U for universal, such that, so for every diagram group D countable, so D is a subgroup of U. But now U, it's possible to decompose it as a semi-direct product between a RAG and F. It's actually quite related to this short exact sequence. The proof of this short exact sequence is proved using this kind of statement. And now this group is biordurable, this one is, and you have to check that it's possible to extend these biorders through the semi-direct product, which is not obvious, but the decomposition is completely explicit and you can do it. It's possible. So it's not entirely satisfying. There is another point of view when you can construct explicit actions on the line. Is so you have your diagram. So let's say it's A, B, A, B, and you have a spherical one. Let's say B, A, and A square, and AB again, ABA, ABA, okay. And now what you can do is you can imagine this line as a copy of 0, 1, this line as another copy of 0, 1, and now for each two cell you will fix a homeomorphism from the sub-interval to this interval, and you will push it to get a homeomorphism to 0, 1 to 0, 1. And so for instance for Thompson's group F, there is a natural, so this is X, X, and X. The natural map is, so you have a homeomorphism from 0, 1 to 0, 2. So something natural to do is just a multiplication by 2. And when you perform this construction to Thompson's group F, you recover its natural action on 0, 1. So you have such constructions. However, there exist diagram groups when it's not possible to get a faithful action on the line from this construction. So it's more explicit than this approach, but it does not work all the time.
Okay, so maybe we stop here because the next talk by Nicolas Bittard is in 2 minutes. So we have a very short break and then we will have a real break after Nicolas' talk. Thank you very much, Anthony.